Hello everyone, my name is Singh and I'm a PhD student at the University of Luxembourg. Today I'm very excited to share our recent work called Discriminator-Free Unsupervised Domain Adaptation for Multi-Label Image Classification. Introducing the problem of multi-label image classification. It's a problem that aims to predict the presence or not of multiple objects in an image. It is much more complex and practical than the other simpler types of classifications like binary classification and multi-class classifications. Existing methods make use of deep neural networks in order to achieve the impressive performances. However, despite of these performances, the real-world application of multi-label image classification suffer from the problem of domain shift. It's a problem where the training and testing datasets belong to different domains, and as a result, the generalization of these MLIC methods to unseen domains is very poor. A deep learning model trained on a labeled dataset coming from source domain fails to generalize well on a slightly shifted domain dataset, also known as target domain. In order to solve this problem of domain shift, one straightforward way is to retrain the model with the target domain dataset. However, that requires the target domain dataset to be hence, to avoid these costly annotation efforts, unsupervised domain adaptation is a plausible solution for tackling this problem of domain shift. The, the concept of unsupervised domain adaptation aims at minimizing the domain shift by using both labeled data from a source domain and unlabeled data from a target domain. There are two components in the end. The multi-label classifier aims to classify the source samples correctly, and there is a domain alignment component. Currently, adversarial-based methods are among the most successful UDA methods for both single label and multi-label image classification. A discriminator, they make use of a discriminator, a domain discriminator that distinguishes between the domains of source and target. The discriminator is trained using a min-max game, and the goal of the feature extractor is to fool the discriminator in order to generate domain-invariant feature. Despite of the great success of adversarial-based unsupervised domain adaptation methods, the two tasks of classification and domain alignment are decoupled due to the use of an additional domain discriminator. This might lead to the mode collapse. In a recent work, the authors have proposed to reuse the task-specific classifier as discriminator. They define a new adversarial critic from the classifier itself, which is based on the correlation of probability predictions from the classifiers. However, the same approach cannot be directly extended to multi-label image classification due to the difference in the nature of the two problems. For example, to compute the correlation matrix, the sum of predicted probability should be equal to 1, which is not the case in multi-label image classification due to the application of a sigmoid activation function in the end. In this section, I will detail the proposed approach. As a first step, we try to intuitively visualize the difference between source and target prediction in the context of multi-label image classification. As we can see in this image, in the histogram of the classifier probabilities for both source and target, two separate clusters can be visualized, one for positive labels that are present in the image and another one for the negative labels that are not present in the image. Also, we can clearly see the difference between the classifier probabilities of source and target. The cluster of the source is very well separated and more centered towards 0 and 1 due to the presence of supervised learning. However, this is not the case in the target dataset. This happens due to the problem of domain shift. Now, the idea is that the distribution of the probability predictions can be leveraged for defining a suitable adversarial critic. And this critic can be directly derived from the classifier, which will avoid the use of an additional discriminator. As a next step, we fit a two-component Gaussian mixture model on both source and target predictions. Each component refers to the positive and negative labels present in the image. A statistical distance based on the Frechet distance is computed between the respective clusters of source and target GMMs. This is the overall architecture of the proposed approach. The CNN-based feature extractor receives the images from both source and target domain to generate the discriminative image features. The classifier performs two actions simultaneously of classification and domain discrimination. When acting as a classifier, it aims to correctly classify the source samples using a supervised task loss, and when acting as a discriminator, it computes the proposed GMM-based discrepancy to implicitly minimize the domain gap between source and target domains. In order to evaluate the performance of our proposed, we make use of three different types of domain shift. The cross-sensor domain shift contains three multi-label aerial image datasets, namely AID, UCM, and DFC. Each of these datasets have been captured using different equipments and in a different environment. This gives a good example of possible domain shift between source and target. We have sim to real domain shift, in which we use two multi-label image datasets, Pascal VOC, which is a real dataset, and ClipArt, which contains 1000 images of simulated environment. The third and the last domain shift that we have considered is cross-weather domain shift. In this, we use two widely used urban street dataset called Cityscape and Foggy Cityscapes, originally proposed for the task of semantic image segmentation. We manually create multi-labels for these two datasets and evaluate the performance on this dataset. In order to quantitatively compare our method with the existing methods, we considered three different types of settings. The first setting is multi-label image classification, which uses no domain adaptation. And then we have the discriminator-based methods and discriminator-free methods. We compare the number of model parameters and mean average precision obtained from the existing state-of-the-art method and our proposed discriminator-free method. For the cross-sensor domain shift, as we can see, being considerably smaller or compact in terms of model size, our method outperforms the existing methods in terms of mean average precision. The similar trend is followed in other two types of domain shift, where a considerable improvement in terms of mean average precision has been noticed while keeping the overall model size smaller. We perform a qualitative analysis where we compare our proposed approach on some of the image samples, where we see that our method is able to successfully predict all the multiple labels present in the image. Finally, to conclude, in this work, we propose one of the first discriminator-free strategy for unsupervised domain adaptation in the context of multi-label image classification. The proposed approach reuses the classifier as a discriminator, which is based on a novel adversarial critic, which is deriving directly from the predicted probabilities of the multi-label classifier. The approach achieves state-of-the-art results under three different types of domain shifts while considerably decreasing the overall size of the network. In future works, we aim to investigate a fully differentiable critic to minimize the domain gap between source and target domains. Thank you so much for your time and attention. Please feel free to reach out if you have any questions.